All right. Okay. So, good morning. My name is Brianna Green, and over the summer I worked with Dr. Nikki Lewandowski, and we looked at ocean acidification variability in the California current. So to start, I want to explain what exactly ocean acidification is. So when atmospheric CO2 is absorbed by the ocean, it reacts with it creates a reaction that results in carbonic acid and releases free hydrogen ions in the water, which reduces the potential hydrogen in the water, or the pH, and makes it more acidic. So for reference, I've included this pH scale just to remind you guys that it ranges from values 1 to 14, where a value of 7 is considered neutral. You can think of your drinking water, or at least that's what it's supposed to be. And values lower than 7 are considered acidic, so you can think of things like lemon juice or battery acid. And values above 7 are considered basic, so like most cleaning products. And it's important to note that the pH scale is logarithmic, so any small scale changes reflect larger scale changes. So taking, for instance, the average ocean pH, which is 8.1, if we dropped it down to 7.9, that's reflecting an 150% increase in acidity. And although 7.9 is considered a neutral value, because the difference is dropping and it's becoming more acidic, we consider it to be growing in acidity, and that's why we call it ocean acidification. In the California current, we see this transition. We see a rapid decrease in surface pH over time. And in a study done by Gruber and others in 2012, we see in pre-industrial times from 1750, 8.2 pH in the surface waters. And then in modern times, we see a decrease to a pH value of 8 in 2005. And by 2050, it's projected that we'll see pH values as low as 7.8 within the next 30 years. So with increasing acidity, this reduces the amount of carbonate ions in the water. And we care about this because most calcifying organisms, such as pteropods, use this carbonate ion concentration in the water to build and sustain their shells. And when there's not enough carbonate to cling on to, they can't sustain, and it reduces their growth in the water. So we measure this by using the ragonite saturation state, which describes the amount of carbonate ion in solution with respect to aragonite. So if you remember in your beloved mineralogy class, aragonite or calcite is a soft mineral, and it's very sensitive to acidic solutions. So in aragonite saturation states that are above 1, we consider to be supersaturated. So pteropod shells have enough carbonate ion to grow and also sustain their carbonate structure. However, saturation states that are equal to 1 or lower than 1, their biological and physiological responses aren't well understood. And that is concerning because we don't know the impacts of rapid increases in ocean acidification, and we want to characterize how these changes will affect biodiversity and also how they will impact California's commercial fisheries in this region. So in this photo shown, it's an experiment done by NOAA in which they exposed a pteropod shell to undersaturated waters. And as you can see, in a little over a month, the shell goes from being completely intact to almost completely deformed. So this brings me to the research goal of this study. And we wanted to characterize California current ocean acidification both spatially and temporally. So specifically, we wanted to see how ocean acidification varies in open ocean and near shore. And we wanted to see whether these changes were seasonal, annual, or interannual. The method we used data from 2 buoys deployed by NOAA in the California current. CCE1 was our buoy that was located in open ocean, and CCE2 was our buoy that was located in near shore. And together, these two buoys both collected PCO2, pH, and other seawater surface parameters. And this data was available at the National Center for Environmental Information. So specifically for this study, we used PCO2 and surface seawater pH, and also salinity and surface seawater temperatures. And we inputted this into the computer programming language Python, and using the package, the carbonate system solver, to calculate the ragonite saturation state at the surface over time. So based off of our calculations for the ragonite saturation state, we were able to create a time series in which we created a time series for both buoys, and we compared the two. So looking at the results at the open ocean buoy, we see the values were continuous over a shorter range of time due to issues with the open ocean buoy's pH sensor, resulting in poor data return. Looking at the results for the open ocean buoy, though, we nonetheless created a time series where we have saturation state on the y-axis and time on the x-axis. And here, the values range from 2.3 to 2.75, and the mean surface aragonite saturation state was 2.5. So this is considered supersaturated, and this is pretty good, actually. And so, as you can see, the values don't really vary very much within the open ocean buoy. Looking at the nearshore results, we had data over a longer period, but the data was discontinuous, again, due to issues with the pH sensor. But, however, we still created a time series. And here, we looked at the surface aragonite saturation state from 2014 to 2017. And here, we can still see a trend where it's kind of like going in this wavy motion, just like in the open ocean buoy. And here, from the year 2015 to 2016, we see a spike in saturation values. However, it's also important to note that in this buoy, we see a lot more variation in the aragonite saturation state, where we have values that are above 4.5 and values that are below 1.5. So comparing the two buoys spatially, we see that variability is much greater near shore than in open ocean. So in this figure, I depicted the open ocean data results with the nearshore data results. And as you can see, the open ocean is pretty stable compared to the nearshore buoy. And also to represent this variability, I also composed a bar plot where we have pH on the y-axis. Okay, where we have pH on the y-axis on this side, and we have PCO2 and surface aragonite saturation state. And while the pH and the saturation state values were nearly identical at both locations, the variability was 14% more greater in the nearshore buoy. Looking at the results over time, we see that we see again this spike in saturation state. And now we may be wondering, what's driving our results? Why is there more variability near shore, and why do we see a spike in the saturation state from 2015 to 2016 and not anywhere else? And this is due to upwelling in the California current. So, upwelling events in the California current are driven by surface winds that blow parallel to the shoreline and drive ocean circulation, bringing colder, deeper, more acidic waters from depth to surface. Additionally, surface winds and changes in seawater surface temperatures driven by the El Niño Southern Oscillation climatic pattern, or the ENSO, contribute to weakened or strengthened upwelling events. So where we have phases of warmer surface water, the upwelling events have a harder time mixing with the warmer surface water at the top. Therefore, it creates a natural thermocline in the ocean, which is why we saw high values from 2015 to 2016 at our nearshore buoy, because there was since it was warmer, there wasn't any there weren't more acidic waters being upwelled. However, in reverse to this, we have in La Nina cycles, we have colder surface water temperatures, and this allows for not only the atmospheric CO2 to be dissolved more easily into the water, it allows the deeper upwelled water to mix more easily with the surface water. And that's why we saw low values also as well as the nearshore buoy. In conclusion, upwelling is stronger nearshore than in open ocean, contributing to greater variability. And the surface ragonite saturation state variability is primarily interannual, as the warming and cooling phases in the El Nino Southern Oscillation happen on a time frame between 3 to 5 years. So with that, I would like to acknowledge the UNAVCO staff for their support and the Ocean Biogeochemistry Group at CU Boulder. I would also like to thank the National Science Foundation for funding this research project and program. And with that, I will take any questions.
Thank you, Brianna. Questions for Brianna? I mean, I know she did a great job.
Great talk. Thank you very much. So going back to El Nino years, so during El Nino years, or an El Nino situation where there's warmer water against the California coast, and that causes upwelling?
No, upwelling is a separate event. Yeah, sorry if I didn't make that clear. Yeah, upwelling happens regardless, and that's because of surface winds. They happen no matter what, whether it's an El Nino or La Nina year. And that's why water is cold in California during the summer. But yeah, but they're two separate events, so it's not like one is causing the other.
Okay, then the years where you do have the El Nino, are you seeing any change in the data for that?
For the El Nino? Because the data was not over a longer time frame, it was harder to see that, really. But from 2015 to 2016, that was the El Nino where we had warmer surface seawater. And that's why we saw the high surface aragonite saturation state. So
one more quick question.
Yes.
If you were a commercial fisherman or you were talking to commercial fishermen, what would be your recommendation on those years where we have that, increase or decrease in aragonite and more ocean acidification?
Fish somewhere else. There's more fish in the sea, so it's a wide ocean. So, yeah. Yes, exactly. So, yeah.
Any more questions for Brianna? No? All right, well, thank you.